vector may not actually slice through a large fraction of the AGN population. So how do you find them in that case? So it's very challenging, and you need multi-wavelength observation. Right? So how do we find AGN? Given what we've discussed to date, how would you propose to detect a large sample of AGN, either locally or at high redshift? So radio, that'll get you 10%. Infrared, that will, okay. Infrared is not too bad because it's a reprocessed emission. But are there any things that compete with infrared? Well, the X-rays don't compete with infrared, but in terms of the processes, there's the host galaxy, you still have an issue, right? Because the host galaxy also emits in the infrared. So the X-ray. The X-ray is better because the host galaxy is much, much weaker compared to the AGN. And so the contrast is much better. You can go much fainter into the population. X-rays are also good because you can see almost most of the obscured population. The infrared is also good in the sense you can see the obscured population. You can detect X-rays for high Z. I mean, we see the alpha OX relation, and it seems constant out to redshift 6 for quasars. Finding things at lower luminosities is not as trivial, and we'll see that tomorrow a little bit. Okay, so maybe an infrared survey, maybe an X-ray survey. We don't want to do it in the optical. Well, unfortunately, the optical is where we have all of the telescopes down on the ground. It's pretty cheap to do it, but it's, as you imagine, kind of biased. And so ideally, you want to do an infrared or an X-ray, observation, but that's expensive because you need telescopes in space to do that. And the technology is such that you can't necessarily do a wide and sensitive survey. You either have to do one or the other. And likewise with the infrared. Okay, so this is kind of a graphic showing essentially a host galaxy, which is seen here in gray, and embedded in it is an AGN. And initially the AGN is not very powerful at all, very low luminosity, and so you don't really see it, right? And so as you crank it up in sort of luminosity, so now here's a faint AGN. You start to see it in the UV first, and the X-ray a little bit, and then into infrared. And as you crank it up in terms of luminosity, you start to see it everywhere, right? So the infrared actually comes in last. And so it's harder to see. You basically see the most luminous objects in the infrared, but you're biased by lots of star formation otherwise. You also see, we probably should, there's lots of things going on here, so we can focus on individually sort of wave bands. So in the X-rays, you see that there's a power law here, and then an absorption term. And as you increase the absorption, you still see the AGN here up until very high column densities. But you start missing it in the soft X-rays very quickly. And so essentially this is a column density of about 10 to the 21. You just don't see it all in the very soft X-rays. And the column density of 10 to the 21 is about a visual magnitude of extinction of about 1. So 1 magnitude of extinction equals roughly 10 to the 21 centimeters, square centimeter, inverse square centimeters of column density of neutral hydrogen. So there's a huge contrast here, which is good. 2 or 3 orders of magnitude, which is very useful. In the UV, you don't see it at all. This is because even a small amount of dust will absorb the UV. So the IGM essentially can eat away this. But you do see it in the optical. And then as you increase the obscuration, you miss it, and you just end up seeing it sort of here in the near infrared. You see that the lines remain for a longer period of time. So if you can measure emission lines, you have a better chance of seeing the AGN even when it's completely obscured. Because there's some lines of sight for the UV emission to get out and ionize the ISM. And so those pathways let UV photons out, there's ionization, and the ionization then is sort of scattered in your direction, or it's scattered in all directions. And then finally in the infrared, you have this sort of hot component, but you have all of these other sort of contaminants as well. And so it's a bit tricky. Okay, so thinking about all of that, then it seems a little, maybe a little bit more obvious that we would want to go in the X-rays most optimally, except for the fact that we will end up missing at sort of 10 to the 25. We will start to miss the X-rays. Even the X-rays go down by a factor of 5 or 10. So we miss those objects in a flux-limited survey. Okay, so we've sort of said all of the takeaway points of this. Obscuration is super important. It affects the UV, it affects the optical continuum, it affects the broad lines, which are embedded very close to the AGN. It has a range of effects in the X-ray, but if you have a hard enough X-ray survey, so if you go into the high enough energy band, it doesn't affect it too much. Little effect in the mid-infrared. Host galaxy contamination is also super important in the sense that we can only see highly or strongly accreting high mass AGNs in optical or infrared. We have strong host contamination in those bands. And it's harder to discern weakly accreting or low mass black holes. And so it becomes tricky to do that. Okay. So we can think about the different tracers. Here's the optical colors. It's okay for very luminous sources, but it's biased because we miss the obscured fraction. Right? So anything that's sort of mildly to heavily obscured, we're going to miss it with these color selections. We can also do SED fitting and maybe get a little bit better, but sort of the same thing. We're looking for a component that isn't the stars. Right? And so that's fine. You essentially are going to suffer a lot because not only do you have the issue of missing the obscured fraction, and also contamination from host galaxies, contamination from stars in some cases. There's certain redshifts where stars become very, very strong contaminants in the color selection, as you can see here. So if you just have a few colors, sometimes you can end up having lots of stars. So that's a potential problem. This leads to strong redshift-dependent selection effects, even with mild obscuration or contamination. And so this is from Sloan. This is, as a function of redshift, the number of objects that are surveyed or found via selection, the color selection technique. And so you can see in DR7, one of the early data releases, which was just going off of the sort of first year of imaging and taking spectroscopy, you see a broad sort of distribution, but there's a big drop between redshift 2 and 3, which isn't necessarily physical. And so, but you wouldn't know that unless you understood your biases very, very well. And so you have to run your selection function through all of the different cuts that you're making in color and in all of the different properties of your survey to understand if you're missing objects or not, to correct for it. You can see in DR12, then they actually targeted certain regions where they were biased. Try and correct for that, or in this case, overcorrect for that. So one of the things that's sort of important here is that this is all sort of done based on optical imaging with a seeing of around 1 to 2 arcseconds. And so it's difficult to potentially resolve lower accretion rate sources from their host galaxies. And so you just miss those altogether. You need very, very bright sources that outshine their galaxy by a high contrast level, 5, 10. As imaging becomes better, either through ground layer AO or through space-based wide field imaging, you'll be able to remove the host contamination better. And so you can kind of carve out the nuclear region and just worry about the contamination there rather than the whole host galaxy, which is what the past surveys have had to deal with. So better spatial resolution can help you push down in luminosity. It can't help you with the obscuration too much, but at least one vector is better. Things to look out for are LSST in 2 years or so. They'll start doing commissioning. W1st in 2025 or beyond, depending on when they actually get funding for it. But that will give Hubble-like resolution over sort of survey-like fields. So the field of view of W1st is supposed to be relatively large, I think 20 arc minutes or something. So it's going to be able to survey large portions of the sky at 0.1, 0.05 arc-second resolution, something like that. And so you'll go from, this is an image of a local galaxy, NGC 1068, and just combining the I and the K band. And so this is sort of the seeing at the moment, gives you kind of that. And you'll be able to push down here and kind of be able to drill out where the source is. And so rather than being contaminated by this, you might be able to say, okay, the AGN is in there, and what are the colors of that source? You can do it a lot better in the K-band, as you can see, because you're not obscured. Right? You've already gone in, and so rather than dealing with 10 magnitudes of extinction here, you might only be dealing with 1 magnitude of extinction in K. So going to the near-infrared also is beneficial. The other tracer that was pretty decent was the mid-infrared colors. It's good. It covers, it's not obscured, well, it's not biased to obscuration, but it's limited in terms of its luminosity. And so this is a couple of different methods of how you would do it. So typically the mid-infrared has the better spatial resolution, but still it's a border arc-second, 5 arc-second resolution. You have pretty strong contamination from your host. So you can do colors again. So this is Spitzer, and so these are the IRAC colors. And essentially the AGN end up being sort of in this region, and the galaxies end up being in this region, and stars are sort of down here. And so you can sort of make a wedge, and there are 2 different wedges, the Lacey wedge, the Donnelly wedge, there's a Stern wedge as well, all to kind of select out your high luminosity AGN, which pop out in this color from the host galaxy population. Spitzer was a relatively small field of view. Didn't have, so it surveyed very, very sensitive observations, but not very wide. And so we have WISE, which surveyed the whole sky, also in the mid-infrared bands. And so WISE color selection uses W1 minus W2, which is the same as 3.6 and 4.5, and then W2 minus W3. W3 is 12 microns. And so again, you have the host galaxy population. This is actually a little chart to show you what's going on here. So you have stars, which are over here, which are largely missing from this particular survey because it was a high galactic latitude. Then you have starting ellipticals, spiral galaxies, starbursts, and lurgs. And so that kind of makes up this population here. And then you have QSOs here and obscured AGN here. And so you can kind of, again, make a little wedge and select them out. Yeah. You're less biased by it. Yes. Sometimes you can't. Sometimes the distinction is hard to make. You can look in the optical, and if the optical is giving you an indication that there's a strong star formation, essentially if it has a very blue component or if it has certain emission lines, you might be able to then say the mid-infrared we should expect there to be some dust and therefore also have star formation. So you can use the full SED to do it, and so in fact, SED fitting is better because you're taking in more information. Right? And so this is an SED fit showing you essentially the colors with WISE, which are right here, and the optical. And so you're able to sort of fit multiple components and figure out exactly how strong the AGN is compared to the host galaxy. Um, so it's actually fairly robust versus obscuration because the difference between a torus, which is sort of face-on versus edge-on, is only a factor of a few at 12 micron. And so you'll still see it. Even, so if you have a very strong AGN, it's going to rise above the host galaxy in both cases. Okay, as with the optical, the better the resolution, the easier it is to remove the host galaxy contamination. The resolution at the moment is a few arc seconds up to 5 arc seconds for Spitzer or Ys. But we have JWST coming, which is going to be able to drill into galaxies to sub-arc second scales, 0.1 arc second. And so you will be able to pick out AGN much, much better by removing all of the host galaxies. And so locally, we might be able to have new estimates of AGN fractions from this. But more likely, JWST's field of view is terrible. It's very tiny. It's not a survey instrument. And so Euclid will survey the entire sky. And it's going to have resolution. It's a near infrared, not far infrared, but it'll have a resolution of 0.1 arc seconds or so. And so there you can get near infrared colors and get AGN samples over the entire sky. So Euclid is coming in sort of 2022 or so. JWST, who knows? In theory, it was supposed to have already launched, but 2022 or so as well. Then you have the X-rays. The X-rays are very good because effectively you can see AGN even when it's impossible to see it in the optical. The X-rays are very penetrating, so you can probe relatively obscured sources. To give you an idea, at 2 keV, 10 keV, or 30 keV, you can probe column densities up to 10 to the 23, 10 to the 24, 10 to the 25. And for comparison, the conversion between AV and NH is 2 times 10 to the 21. So effectively, 10 to the 23 is probing something like an AV of 100. So that's, you're never going to see anything here, and all of a sudden you can easily see it, even in relatively sort of soft X-rays at 2 keV. And if you have a hard X-ray survey up to 30, you can see pretty much everything that isn't fully just optically thick. So the relative contributions are also smaller from host galaxies, so the contamination is better. You can probe down at least an order of magnitude or 2 orders of magnitude deeper into the luminosity, the accretion rate, effectively, for AGN in the X-rays versus the optical. So we can actually probe the low luminosity, low Eddington rate regime. Several surveys have already been up. There's the Swift-BAT survey, which is a hard X-ray survey, which did all sky to modest sensitivities. There's Chandra and XMM, which are pointed observations. One interesting thing on the horizon is eRosita, which is going to be launched next month. And that's going to be an all-sky survey, taking essentially 4 years to sort of be done. And it will probe an order of magnitude deeper than our current all-sky survey. And so it's going to generate several millions of AGN. Now, we'll have to actually follow them up. We won't know what distance they're at, but it will essentially give us a very large sample to make a census of AGN with. The next generation of sort of very powerful X-ray telescopes are all plus 10 years away. So Athena, what's the other one? There's another one which is the Constellation X, or it's a new version of that. Anyway, they're all lots of planning. Okay, the radio. So the radio is okay. You don't have much. You have some contamination from star-forming processes. In fact, you have supernova, which drive cosmic rays. The cosmic rays filter out, and they interact with the magnetic field in the galaxy, and that produces synchrotron radiation. And so you have some diffuse component which can contaminate the emission. So generally, if the source is what we call radio loud, and radio loud means the radio flux at 5 gigahertz, for instance, is much brighter than at the optical. So by a factor of 10, then it's easily seen, and you can classify it as a radio loud AGN. Now, with the technology of the day, we can go down deeper than that. We can go down the sort of radio intermediate objects. So R of 1, or maybe even R of 0.1 or 0.5, before the contamination from the host galaxy really starts being a problem. Again, the resolution can help, right? If we just can narrow it down to the central core, we can probe down to sort of fainter luminosities for the radio. The other big issue, of course, is that only 10% of AGN seem to be radio loud. Some fraction are radio intermediate, and the majority are radio quiet. And we don't exactly know the full regime and parameter space of the radio quiet. Probably all of the AGN emit some radio emission from the central nuclear region, but it's difficult to discern that from the star formation that's going on around it. Right, so you have some radio quiet objects have tiny jets. 1068s, Circinus have jets. We can see them because they're right in our face. They're very close. Right, so in terms of what's on the horizon, actually there are surveys right now being done. ASCAP in Australia, MEERKAT in South America, the VLA All-Sky survey are taking data right now, and so we will see in the next year or two some of the early data sets that come out of this. And this will be a huge jump in terms of sensitivity and in terms of number of AGN that are radio intermediate. Finally, you have emission lines. And the emission lines are actually very good because if there's a path out in any direction, you'll get some ionization, you'll be able to see that emission line. And the emission lines, hopefully, maybe, have you guys seen this diagram before? Never, okay. So this diagram is tracing several emission lines. So these two emission lines here, there's nitrogen 2 and H alpha, and that's the ratio of these two. And then there's O3 and H beta, which are these two, and H beta is down here. And so one of the critical things is in the optical extinction is very, it's a strong effect. So you want to take a ratio between lines that are very close together, so there's no extinction effect between that ratio, right? If you extinct the galaxy, you'll extinct both of these lines the same, and the ratio remains the same. It's fainter to detect, but when you detect it, the ratio is preserved. So the idea is these particular lines, the oxygen 3 lines and the nitrogen 2 lines, are sensitive to UV radiation, and in particular harder UV radiation, higher energy UV radiation. And so generally for stars, the ratio of these objects falls in this sort of curve right here. And so you have low metallicity, very young star formation up here, and sort of a little bit older star formation down here. And so if you move off of that locus of points, you have a different UV radiation field that's powering or pumping the emission lines. And you tend to move up in this direction because it's a harder UV radiation field. So you can have shocks that will do that. And so some of these objects here are from shocks. So the gas is shocked, and that heats the gas up, and you end up with emission line ratios which are a little bit hotter than the normal H2 region. And then you have very, very strong UV radiation fields which are dominated by the central engine, the nucleus, the accretion disk. And so there you push all of these objects up. And so, in fact, you can think of this as a sort of scale, and so the relative contribution from the host versus the AGN. So if the AGN is just completely dominating the emission lines here, you will sit up here. If it's contributing kind of equally, you'll sit sort of here. And if it's contributing just a small fraction, you'll sit down here. And so you can use some cut to select your AGN population. And this gets you a large number of sources. And it's sensitive to both obscured and unobscured AGN because both of them have these narrow lines. And so it's pretty robust against obscuration effects. You can go very deep into the accretion rate. So you can go to low accretion rates with this as well. So it's very powerful, but you have to get spectra for all the sources, which is expensive. As we're sort of coming to the age of multi-object spectroscopy, and you're getting massively multiplexing instruments where you can observe several thousand objects at the same time, you're starting to build samples of galaxies and the nuclear portions of galaxies where you can do this kind of thing and select AGN this way. So this is becoming more powerful. There's Sphere X, which is on the horizon, which is actually a space observatory where it's going to get IFU coverage of the entire sky. Yes?
The BPT diagram is useful even for highly obscured galaxies?
So at some point, you start obscuring all of the lines. So if you have something which is almost optically thick, you don't have any pathways to get out, then you miss those lines. And so it suffers about the same as the X-ray in terms of being not so sensitive to the very, very obscured objects. There, what you would want to do is go into, this is the optical range here, so you would want to go into the near-infrared or even the mid-infrared, where you can see essentially embedded emission lines, and because there's no obscuration anymore. So high ionization lines in the mid-infrared are the most sensitive tracer to obscured, very, very obscured emission. But if you want to make just a census of the overall population, this does pretty well. I mean, this is why I say very good, not excellent, not perfect. Nothing is perfect. That's the problem. Or it's very difficult to get those observations. So in addition to being able to trace the narrow lines, you also, of course, are sensitive to the broad lines. So you can make distinctions between unobscured and obscured AGN. You can look at the obscured fraction and how it changes. You also have the strong ionization lines, sort of mentioned these two, but you also have neon, you have iron, and you have certain species of those, and that actually tracks the strength of the UV radiation field, how the slope looks, how many photons are being generated at very, very high energies versus moderate UV energies versus low energies. So you have the ability to actually trace properties of the disk if you have enough signal noise and information in the spectrum. You do suffer some from star formation as the AGN becomes weaker. You can also, in addition, these are optical ones. We use the optical most because it's best calibrated. And of course, we have lots and lots of historical sort of modeling of it and everything. But there are lines in the UV, there are lines in the infrared that allow you to make this distinction as well. And so if you had thousands of infrared spectra, you could do pretty well. The problem is it's just very expensive at the moment. Okay. One of the other problems with this is that this is the optical. And what happens if you want to observe an object at redshift 2? This leaves the optical. The H alpha is at 6563. So it leaves the optical band, say 9,000, say 10,000, at around redshift of 1/2. And so you get a local census, but you can't use this diagram past redshift of 1/2. This is at 5,000 angstroms, and so past a redshift of 1 or so, you can't use it in the optical. And so this BPT diagram, at least as it seems right now, is only useful for kind of the lower redshift end of the universe. The last 33 gigayears or so, or 5 gigayears. So people have tried to think about different classifications which use lines which are seen in the rest frame sort of V or U band, or even the near infrared, or sorry, not near infrared, near ultraviolet. And so the neon is at sort of 3,000 angstroms, O3 is at 3,700. Neon 3 is actually around 3,700 as well, 3,600. And so you can use this ratio along with a color to select AGN. And so this was known as the TBT classification for the lead authors there. But you can play these games where essentially what you're doing is trying to find unique lines which are relatively bright, which tell you about how the UV ionization field looks. and if there's an active galactic nuclei there or not. That's the main point. So you can use these tracers up to higher redshifts with the optical spectrum. The alternative is to get near-infrared spectra, and then you are essentially tracking the same lines, these lines, out to redshifts of 2 or maybe 3 in some cases. Essentially, H alpha you can see in the K band out to redshift 2.5 or so. Okay. Finally, the last one is the one we talked about yesterday, which is variability. Right? And so AGN are variable. And variable selection is actually very good at finding low luminosity AGN. Why is that? Because we can just take a difference image. We can take one image from one epoch, an image from the second epoch, we can subtract them, and the host galaxy falls away, and the variable component stays. And so you see a nuclear variable component, and you say, oh, okay, voila. The other benefit, of course, is that the low luminosity AGN vary more than the high luminosity AGN. And so they're easier to see in this sense. You still have, when you take a difference subtraction, you still have noise because initially you had very high, high levels of flux. So there's still some problems with the contamination, but it's much diminished from just the optical color selection. And the benefit of this is targeting a regime which is completely biased by all the other indicators. So you can use this in tandem with the other indicators to try and pick up some of the lower luminosity sources. Right? And in fact, the ideal thing is you throw all of these indicators in a bucket, and you end up with a huge AGN sample. Interpreting that is not easy because you have 30 different selection effects, but you have an overall census of the population, or the best census of the population. So if you just want to find them, that's fine. And add them in and try and figure out the selection effects. Okay. In this regard, you still have the issue of obscuration. If you are obscuring the nuclear region, if it varies or not, it doesn't matter because you're never seeing it in the first place. So it's still biased, but it can probe lower luminosity. ZTF, the Zwicky Transit Factory, is operating today. It just released its first data release, and it's essentially observing a large fraction of the sky with multiple epochs, and so you can actually track and look for low luminosity AGN in them. LSST, of course, will be much more powerful. ZTF is delivering typically given images to about 21st magnitude, so you can think about essentially it's reproducing the digital the digital sky survey every time it observes. Right? So you're getting to that sort of depth. LSST, when it's operating, is going to instantly, in 30 seconds, take an image to 24.5 magnitude, which is more like a relatively shallow image on an 8-meter telescope. But that's 3 orders of magnitude, 3 magnitudes deeper than PAS, or the Digitized Sky Survey. That's an order of magnitude in terms of flux. So it's very powerful. And so you'll be able to probe a huge new population of moderate luminosity, low luminosity AGN with LSST. Okay, so you put all of those things together. And so in the optical, we improve a little bit using other techniques. And so rather than the 1% of galaxies that were Seyferts before, you might be able to bump that up to 5%. Because you can probe a little bit lower luminosity. You have the line diagnostics to tell you that there's an AGN there. And so something like 5% of galaxies in the optical are AGN. And so this is just showing as a function of black hole mass the percentage of systems that are AGN in the local universe, and this is the optical here. And so you can see it varies a little bit depending on the black hole mass. You are a little bit less sensitive, or less sensitive to lower black hole masses, but it's about 5% on average. Kind of flat. If you use all of these other techniques, you can end up bumping up this fraction modulo there are big error bars, but potentially we're talking about maybe between 20 and 30, maybe up to 40% of the population are accreting, and you can see it. It's a much bigger fraction. It also means that, you know, the optical kind of sucks because you're only getting, you know, it's a factor of several that you're missing completely. And so, you know, you can be very biased about your interpretation if you're saying, okay, I have my sample and I'm going to make some very profound interpretations about how these objects grew and the duty cycle of AGN and so forth. But if you're missing 4 times as many AGN, you know, you're going to have problems interpreting that. You know, the orientation, how big is the torus, all of those things which you might use with these sort of statistics, they can be completely changing because of this difference. In the optical, we see about 4 times as many type 2s as type 1s. When we go into the other bands, this changes. And so we don't see that as much. We see a more equal ratio at some point. 10% of the AGNs are radio loud, but there's a clear dependence here, right? So this is the sort of X-ray mid-infrared, this is the optical, this is the radio. And so there's a huge dependence on black hole mass, which is what I sort of alluded to or mentioned, but didn't really talk about in the last class. And so for some reason, radio loud AGN only exists around big, massive black holes. There are a couple of reasons that this could be. One is, well, say you make a black hole and you start to feed it. And so as you're feeding it, the accretion is spinning it up. And so you may need the initial black hole, or however they're made, may not have much spin initially. Or you could spin it down to 0 and then you had to spin it back up, depending on how the accretion was flowing relative to the intrinsic spin of the black hole. Right? You could have counter-rotating accretion that would lower the spin. So as you grow the black hole, things may kind of align such that you essentially spin the black hole up to a maximum amount. And so this may also come into play here. So bigger black holes have had a longer time, easier time to be able to spin up to a maximal rate. So that may be one thing. It also may be that the accretion disk, there's something about it that you need the big black hole, so you need the radius to increase somewhat in order to start generating the radio jets. That maybe there's some physics there that you see a transition between the black holes and the accretion disks that are in this regime and this regime. But it's still early days in terms of modeling and understanding that. Okay. So demographics. Where do we see AGN? Well, in fact, which host galaxies do we see them in? This depends on the sensitivity. As I said, sort of 10% of all galaxy types host AGN activity, but there are certain types that host it more preferentially, or it's more obvious. So massive systems, this is now the stellar mass. Essentially, the massive systems end up showing more AGN than the lower mass systems. And part of this is just a bias, because massive systems have more massive black holes, and if you feed the same amount of material to a massive black hole and a small black hole, the massive black hole will look brighter. And so it's just easier to find them here. But there still is a strong bias. You know, clearly there's very few AGN in dwarf galaxies. Another thing that we see is that the AGN fraction is strongly dependent on the infrared. So if you have a very bright infrared galaxy, you almost always have an AGN being fed actively at the same time. So this is the infrared luminosity here, and essentially you can see that there's a peak, and so around 40% of sort of modest infrared luminosity objects are accreting, and you can see them. A little bit lower here, but this is probably biased by obscuration, and so you may actually have a pretty large fraction. And then as you go down to lower infrared luminosity, these typically also are lower mass. You don't see many AGN at all. what is this telling us? Mostly that the AGN are where the gas is. Right? The infrared is tracking where stars are being formed. And stars form out of gas. And some of that gas trickles down into the nuclear region and feeds the AGN. So both of these things are driven by the need for cold molecular gas to lose angular momentum and create stars in one case and the AGN in the other. And so when there's gas, there's both of these processes, making stars and AGN. Okay. So AGN need a turbulent gas-rich host in order to fuel efficiently. What environments do AGN sit in? So again, if you look at the stellar mass, right, we see that the AGN are mostly in these high stellar masses, but you'll also notice that the AGN fraction of basically strong AGN seem to be a little bit more prevalent in low density environments versus moderate or high density environments. And naively, why would this be? Don't know? So the environment has a couple of effects. One is its ability to remove gas from the galaxy. The other is to inhibit gas from ever getting into the galaxy. And so cluster environments are kind of nasty because you have lots of galaxies, there's chances of interaction. So if you have an interaction, if they had gas, you'll be able to strip some of the gas away. You might process some of that gas very fast into stars and burn through it very quickly. You'll heat the gas. So there's all sorts of effects that lead you to have less gas. And so less gas ends up getting into the AGN, and so you don't really produce strong AGN. Whereas in low density environments, you have cold gas that can accrete onto the host at sort of a constant level and sort of feed the AGN pretty regularly over gigayears. So this kind of explains this difference. You also have sort of an evolution in terms of the cluster AGN with redshift, although we're only going up to redshift 0.5 here, and these error bars are pretty big. But this might be because we're now in the age of cluster formation. And as you go back in time, clusters were sort of still forming. And so these processes through which you get rid of gas, you heat gas, were still going on. And so you still had objects which had gas. And so the AGN fraction increases consistent with that. Essentially, by the time you get back to redshift 1 or redshift 2, you don't have many clusters at all. And so almost everywhere is sort of a moderate density environment or a low density environment versus a high density environment. So black holes are growing rapidly in massive galaxies, but only in low density environments. Right? One thing to think about is, so when you have a strong, high accretion rate, that means the black hole is growing rapidly. Right? It's accreting a lot of material, relatively. It's only a few solar masses per year, but if you have that over a gigayear, that's a lot of mass. So if it's not accreting very strongly, then it's not building up very much. Right? It's kind of moving along, but it's really not adding much mass. It's not doubling its mass. It's not going to do something like that. You really need high accretion rates to start adding lots of mass to the black hole and growing it. So this is essentially telling us that black holes will end up growing in low-density environments, do not grow so much through accretion in high-density environments. If the fuel supply, basically the fuel supply ends up being exhausted here, and you never sort of get it back. So this, in a sense, the high-density environments are sort of graveyard, cemetery for AGN, because once they're kind of there, they're not going to grow very fast unless you have a merger and you merge two black holes together. That's how they might grow. But they won't go through too much through gas accretion. Okay, so I'm going to take you through one of the sky surveys, which is sort of a local sample, but it's of high X-ray selection, hard X-ray selection, with the Swift BAT instrument. And so we think it's probably the most complete sample of AGN we have in the local universe. And we can look at some of the statistics from it to kind of bear that out. So this BAT All-Sky survey, or actually the BAS is the BAT AGN Sky survey. It's considered the most complete sample. It has a sample of about 600 to 1,000 AGN, depending on which version of the BAT catalog you use, because BAT's been up for 15 years, and it keeps observing. And so it keeps getting a little bit more sensitive and finding new AGN. But essentially, most of the papers are written on the 600, and then now we have about 1,000 or so. So this is the distribution. And so you can see unobscured, obscured, and what we'll call Compton thick, which means highly obscured. So the column density through it is higher than 10 to the 24. That's what we consider Compton thick. So, and then you also have blazars. So you can see they're all over the sky. There's a little bit of a difference here. The Milky Way kind of goes something like this through it, so there's not too much bias there. There's a little bit of bias in this region where you have high amounts of dust, and so we don't have as many X-rays there. But it's pretty uniform-ish, tracing a little bit of large-scale structure at redshifts of 0.1 or so. If you look at the redshift distribution, so I'm blocking off this portion because it's not really relevant here. The Swift BAT sources are these. It's a flux selection. And so because it's a flux selection, that means that you'll see lower luminosity sources closer to us and only high luminosity sources far away from us. And so as a function of redshift, that's what you see here. So this is just the flux selection. You see that if you sample this region, you don't have a huge volume. And so you may not find a really bright AGN because they're just so rare. And so you have to increase your volume to find one. Right? And so that's just essentially going here and saying, OK, this is a quasar level luminosity, and so I need to go out to redshifts of 0.4 before I start finding quasars. So the most sort of ridiculous big black holes really strongly accreting. And I need to go out to redshift 0.1 to find the sort of even more ridiculous things. And if I wanted to talk about the really super rare things, then I would go over here up to redshift 1 or 2, and you do find a few. But they're very rare objects. There's none in the local volume at all. OK, so you have the regular AGN. You also have beamed AGN, which are the radio blazars. And so they're typically a little bit brighter in luminosity. And then you have a bunch of regions out here. If you wanted to make a full census of the AGN population, it was hard, because if you want to get low luminosity AGN, you have to make the cut here. And then you don't have any high luminosity AGN. If you want high luminosity AGN, you make the cut, and then you're missing a huge amount of faint AGN. And so you need to do something sensible where you piece together you stitch together the different redshift bins or volume bins to make a proper census. You can assume that these AGNs will also exist out here in this volume. We just don't detect them. And if you go to pointed surveys, so some of these are Chandra surveys. The Chandra surveys fill out this region, but they're not very big on the sky, right? They're only sampling a very, very small fraction of the sky versus that. And so you would need to multiply these by the inverse of that fraction. And so, right, if you want to say, OK, the red sources here, they're only a sky fraction of 0.07%. So you would multiply by 0.0007 or divide by 0.0007 to get the right number. So there are lots of them, even though there are a few on this plot. And they fill out this region. So BAS is still flux biased, but that's the only bias it has. And that's a pretty easy bias to unravel, to sort of correct for. OK, so the benefit of this BAS survey is that they're local objects. Most of them already have identifications, already have spectra, already have redshifts. And so 90-some% of the BAS sources already have redshifts. They already have spectra. You can classify the spectra, and then we can sort of turn up with a fraction of type. And so we divide up all the Seyfert galaxies, but the Seyfert galaxies make up something like 85% of the total fat sample. Most of them are AGN, and you see that from the emission lines. Most of them, something like 35%, are Seyfert 2s. Then you have Seyfert 1.9s, which means no H beta, very tiny, broad H alpha. 1.8 is a little bit bigger H alpha, still no H beta. 1.5 is big H alpha, small H beta in the broad line. And 1.2 and 1.1, again, are then slight differences in H beta to H alpha and no differences, essentially the proper sort of ratio of 3 to 1 of H alpha to H beta. You have a few sources where we don't detect any lines, or they're very weak, and so we can't make an estimate. There's still an AGN there because it was detected in the X-rays. But for some reason, it's not driving a lot of emission line in this source. You have a few beam sources, and then some don't have the proper wavelength coverage to make the estimates. If you look at the type 1 to type 2 fraction, as a function of luminosity, and this is the luminosity, the intrinsic band, which is 14 to 195, or this is the observed band, 14 to 195, and this is the intrinsic 2 to 10 keV. And they're pretty similar. Essentially, you see that the fraction of broadline sources increases with luminosity. And so the fraction of type 1 sources increases with luminosity. And this is both for H alpha and H beta. And so at the very extreme, at these sources here, up here, a large fraction, 80% of them, are type 1. Whereas down here, lower luminosity sources, less than half of them are. So that's kind of weird, right? If you thought about an orientation model, you would think, okay, you have a torus, and it blocks a certain fraction of the sky, and it might do that for all sources. But maybe the torus is different depending on the luminosity of the source. For one, you have radiation pressure. So the radiation pressure drives a wind out. And so that wind could sculpt and maybe push down the torus. So higher luminosity sources might have a smaller torus in terms of sky covering fraction. And therefore, any line of sight will be able to see deeper in to the AGN for more luminous sources. This is called the receding torus model. You also can compare the optical classification to the X-ray classification. And so this is done here. So in the X-rays, we classify things by the column density. And so we have a power law spectrum, as you saw in the graphic. And then you have obscuration, which cuts off the soft X-rays. And where that cutoff happens gives you the column density. And we can compare that to the full width half maximum of H alpha. That's telling us if we have a type 1 or a type 2. If we have a broad line, it's a type 1. If we have a narrow line, it's a type 2. And so you can see here, we see lots of type 2s at low column density. And then as you move to high column density, you have lots of type 1s here, which kind of come up at around 10 to the 22. You still have a few where you see some weak broad line from H alpha. But mostly they're Seyfert 1.9s. There's very few Seyfert 1 to 1.8s. And so there's a pretty good correlation between the X-ray obscuration and the type in the optical. And typically in the X-ray world, we talk about unobscured, which are things below 10 to the 22, and obscured, which are things above 10 to the 22 in column density. And then things that are above 10 to the 24, we say they're Compton thick. And so you have those three regimes that you can characterize pretty broadly. And so there's a pretty good correspondence between the optical type 1 and unobscured AGN in the X-ray, obscured AGN in the X-ray, and type 2s or Compton thick AGN. So we can also look at the BPT diagram for these objects. And so you see that the majority of them fall in the Seyfert regime. There are a few that fall in this sort of liner regime, which is low ionization nuclear emission region. These might be due to shocks or some low luminosity AGN process. And then you have the H2 regions, and you can see there's only 2 objects which appear to be completely stellar based on their line ratios, which is pretty good. You have several objects here which are composite, and so it's maybe unclear. Their host is really contributing a lot. The breakdown, again, in terms of fraction, you have lots of Siever galaxies. You have a few liners. You have some composites, H2 region looking, some beam sources, weak line sources, et cetera. Okay, so that's kind of the census. So the hard X-ray does a very good selection. The lines also do a pretty good selection. You've missed very few of these objects based on the lines, but it's very expensive. You have to get spectra for 1,000 sources. Okay, if you compare BAT to the Sloan Digital Sky Survey, which selected objects above magnitude 19 or above magnitude 17, and they took a spectrum of it, the type 1 to type 1 to total fraction, which is essentially the type 1 to type 2, basically the type 1 fraction is about half for the BAT sample, whereas you can see for the Sloan sample, it increases as a function of redshift. So there's clearly something going on here, right? Because Sloan is missing most of these sources. And part of the reason is that Sloan didn't take deep enough spectra to potentially identify the lines in these objects. But there's a strong bias in the way that the Sloan sources were selected. And so that is also coming into play here. But if you take this Sloan sample and you say, I want to do statistics with it, again, you will get a very different answer than if you take the BAT sample and say, I want to do statistics with it, in terms of understanding the demographics. In terms of H beta to H alpha ratio, so dustier things are going this way, and round 5 is essentially obscured. You can see that the fractions between BAT, and these are just narrow line sources, differs with Sloan. And so BAT ends up finding things that are more obscured. And so the ratios may still, the lines may be there, but they may be fainter. You need to observe for longer to see them. So again, there's some biases here. In the X-rays, we have X-ray spectra for all of these objects, and so we can characterize the obscuration. And so the fraction of sources, you can see that there's a sizable fraction that are unobscured, and then a rising fraction that are obscured. And we have to make a distinction between the observed fraction, which is here, and the intrinsic fraction, which BAS is still biased. They still have a harder time finding obscured AGN because they're fainter. And so you'll see fewer of them. So you need to make a correction for that. The fact that you can see some of them is good because you can make that correction. Whereas with Sloan, I mean, you don't know anything about that. So you have a harder time understanding the intrinsic population to correct with. So you make this correction, and so you make a correction for unobscured sources, the fainter ones, and you also make a huge correction for the obscured sources, which are very, very faint. But there's a lot of them. And so you can see that the NH distribution is relatively flat between 20 and 25. And so that suggests that the intrinsic sort of fraction should be, if you cut it at sort of 22 or so, you should have an intrinsic type 1 to type 2 fraction of sort of 40% or so. This is the observed fraction, which is a little bit higher. If you then take this assumption and say, this obscuration is coming from our fiducial torus, the obscuring material around the AGN, you can model that. And so you can say, okay, I see a certain amount of emission if I assume all tori are kind of similar. And so depending on the line of sight, if I'm looking here, here, or here, you might have different cross sections through the torus, and so different amounts of obscuring material, with the most coming from this line of sight. So you can make it a sort of generic torus model, and you can then understand the opening angle that you need to reproduce the data. And so for all of these sources with these column densities, essentially you come away with a model where the torus opening angle is somewhere between 70% and 90%. And this gives the right fractions of sources with these column densities, the different fractions of type 1 versus type 2. So you can now start to use just pretty basic constraints to understand the environment, what the structure is around the AGN, and how that might lead to the physics of feeding the accretion disk that feeds the black hole. The other benefit, of course, is that we have spectra. We have broad lines. We also have information about the host galaxy. Oops, excuse me. And so we can also characterize the bolometric luminosity as a function of the Eddington rate and the black hole mass for many of these objects. And so when we do that, we can see this is in terms of redshift. So there's a clear redshift bias. Essentially, at very, very low local volumes, we can see relatively low, faint accreting sources, so low Eddington rate sources, which are denoted here. And this is kind of the limit of where we can see those as a function of the black hole mass. You can see low accretion sources with high black hole masses much better than low black hole masses, because it's a selection effect. And then as you go out in distance, you go out in accretion rate in this sort of slice. And so you can see here the very high accretion rate sources are dominating at the very large volumes. And the mass range is also a little bit more limited. And then you see the intrinsic beam sources up here, which are at Eddington rates of much higher than 10. But most of the sources are lying well below the Eddington accretion rate of 1. There are a few sources which are about there, but they're a small fraction of the total. So the average accretion rate is more like about 0.1 times the Eddington rate. You can also look at this in terms of Seifert 1s, Seifert 2s, and liners, or low luminosity, low Eddington ratio sources. And so what's interesting is you see that the Seifert 1s seem to be higher accreting sources than the Seifert 2s. And so if you had a pure orientation model, you wouldn't expect this. You would expect to be able to correct the Seifert 2s and find the same luminosity for them. But we also saw that there was this differing ratio as a function of luminosity, right? The so-called receding torus. And so again, we're seeing something like that. So the things that are accreting at higher rate are pushing down their material, and they have a larger opening angle than the lower luminosity sources. So the orientation model isn't the perfect fit for everything alone. You can break things down in terms of black hole mass, in terms of bolometric luminosity, in terms of Eddington luminosity. In fact, actually, most of the sources are not even accreting at 0.1. They're really accreting at sort of 0.01. So they're weakly accreting sources. OK. So you can look at the entire sort of landscape of this plot, Eddington ratio versus black hole mass. And you have the very high accreting sources with very massive black holes. These things are super rare. These are the quasars. Then you have the things that are lowly accreting and low mass black holes. Those are normal galaxies. Those are very common. And you have lots of things kind of in between this that are making up that population that we saw here. And so just to put some faces to this plot, these are some of the local galaxies that might exist on this plot and where they might sit. So you have something like Markarian 331, which is a powerful quasar. We can actually see WIN's feedback in this source. It's kind of sitting up here. And then you have some very, very local objects, which are sitting down here, low accretion rate, relatively low black hole mass. And those are the more common objects that we'll find in the local universe. Just to give an idea, this is the rate if you were to feed the black hole with 0.1 solar mass per year. Right, so coming back to one of the questions of you don't have to feed the AGN very much to see a bright AGN. In fact, the rare sources are only accreting sort of 1 solar mass per year before they hit their Eddington limit. So that's one star, one sun is going into the black hole every year. Not much. And some of these sources, really, pushing this down, this is in orders of magnitude, you have a very low accretion rate needed to power these things. So we can start to push down to find things like our own Milky Way. We can also look at galaxies which seem inactive, and we can place constraints on their Eddington ratios. And so the plot that I was showing you before cut off around here at -4, but we can drill down into these sources with X-ray telescopes and place constraints on their Eddington accretion rates. And so you can see that, we're talking about things that are accreting at 10 to the minus 8 of their Eddington, or 10 to the minus 10. Here's the Milky Way. Here's M31. And so we can start to understand the overall sort of distribution of Eddington ratios for the population of local sources. How often do we find objects that are lowly accreting versus highly accreting? So only something like 5 to 30% of galaxies are very active now, so they're above this plot. And so that's primarily the most massive objects. And so this implies a couple of things. One is that AGN growth is transient, right? So you see a bunch of sources down here, which are lowly accreting, but they have pretty big black holes. How did those grow? They must have grown in the past. And you see some that are kind of actively accreting, but even those accretion rates are pretty small. And so we think that there's a cyclical growth cycle to these AGN. The interesting thing, of course, is that with the Magorian relation of black hole mass to spheroid mass, this means that we can actually probe the black hole masses for all galaxies. We can take the galaxy luminosity function, and we can convert that to a black hole mass function. Or we can take the galaxy mass function, so the masses of all of the local galaxies, and we can convert that to an AGN mass function. So that's what this is here. And so these things, this is the number density, so per cubic megaparsec. And so very massive black holes are very rare. Very low mass black holes are pretty common. And it makes sense. There's lots of small galaxies, very few big galaxies. The integral of this is essentially all of the matter that was accreted onto black holes over cosmic time. This is a pretty hefty thing to think about, right? So it's the sum of all accretion history goes into this. That's a useful constraint, right? Essentially, all of the accretion that we see in the universe, if we are able to sum it up, it should equal this black hole mass, in theory. If it's not obscured. If it's obscured, we have to account for that because we're not seeing it in the integral of all the sources of accretion. So black hole growth events, you have, is it black hole activity a continuous or a transient event? So we can come back to the original source, 3T273. It has an accretion of sort of typically 1 to, in some cases, quasars, 100 solar masses per year. If you integrate that over 13 gigayears of cosmic time, so constant accretion, you would end up with a black hole mass of 10 to the 11. And we see that most of the local black hole masses are more like 10 to the 9, a few 10 to the 10. And so that suggests that we don't need to accrete very much, or that we can have accretion periods which are transient. So the space density of these things is very, very small, so this probably doesn't happen. More likely, you would have this process being cyclical happening over 10 to the 8 years, and then you would end up with a 10 to the 8 solar mass black hole over 13 gigayears. You have periods of activity, then it's dormant, then it grows again, etc. That's at least a basic model. With an efficiency of this, and you would end up with an accretion rate which kind of goes like 0.1 times the luminosity to the 45th power times solar masses per year. An AGN lasts this long, and so effectively during this time, you would accrete something like 10 to the 6 to the 10 to the 7 solar masses. Okay. That's about the size of a molecular cloud. And so you can imagine a molecular cloud somehow finds its way into the center, gets kind of shredded up, falls into the torus and accretion disk, feeds the AGN until it runs out, and then you start the process over again. And so this could kind of just be a natural cycle. And if you have a merger, you send lots of molecular gas all at once. and so you feed it very rapidly, but it's limited by its Eddington-rated growth. So you can see here sort of time per year and the amount of mass accretion that can happen. And so you could imagine if you had a seed black hole of about 1,000 solar masses, it would start off here, and you could have this fuel supply, and effectively this would be its Eddington-limited growth. So it would start off not being able to be fed very much in terms of solar masses per year, and then as it grows, it would be able to be fed more with this sort of limit. And so following that up, this Eddington-limited black hole growth, basically you have balancing the radiation pressure with the gravitational pressure, and so you're balancing these things. And so the E doubling time, so the amount of how fast you can double the black hole mass, ends up being sort of at this rate. So at the Eddington rate, you'll double every 45 megayears or so. And so that would take about 500 megayears to grow a 1,000 solar mass black hole into a 10 to the 8 solar mass black hole if you're accreting constantly. That's not a lot of time, and so that's not too bad. And so possibly the first massive stars made black holes of 1,000 solar masses if there were POP3 stars, and those were then the seed black holes that fed these things. But you know, in order to get this, you need many E-folding times, but essentially one E-folding time is about one growth phase. So you could feed a black hole, grow it potentially by a factor of 2, wait a little bit, feed it again, and eventually get up to that mass. Or you could do it in a sporadic way and feed it a little bit longer and a little bit shorter, so you could have a accretion history which varied. If you look at the luminosity of things being produced now and the black hole mass, this gives you sort of a rough accretion rate. Most of the things were accreting at between sort of 0.01 and 0.1 times the Eddington rate. And so if you were to do that and sort of accumulate that up, you would find that most of the massive black holes had to have grown pretty rapidly in the past versus now. So the low mass black holes are growing pretty rapidly now. The big black holes had to have grown a lot in the past. And so we have a prediction for what's going to happen when we look at high redshift. So let's see. Yeah, small black holes growing relatively small. Big black holes growing relatively weakly at the moment. With galactic archaeology, the stuff that Manuela is teaching you, it's nice because the stars actually trace when they were formed, if they all formed at a similar time. And so essentially you can age date the stellar population. With accretion, you don't have that privilege, right? They have no memory of when they were accreted. You just have the black hole mass. And so we have to look back in time in order to see when they actually grew. We can't just study a galaxy locally and figure that out. So we make surveys. We have the same problem that we do locally. We need to find the AGN. And so we make HST surveys. They're okay for finding unobscured sources. We make X-ray surveys. They're great for finding obscured and unobscured sources. We make infrared surveys, which are also good for finding obscured sources. We combine them all together in the same way, and we end up with AGN. The optical mainly give us quasars, and so we can find quasars all the way out to high redshift. When we do that, we find that the space density of quasars peaks at around redshift 2 to 3. And so that's nice, but it's biased, right? This is only the unobscured sources. We know nothing about the obscured sources, which may be a large fraction of the population. But it's a very effective way of finding AGN out to redshift 6 pretty easily, but you miss the majority of the population. If you make a luminosity function, or a mass function, that's just the space density of sources as a function of the luminosity or the mass, you see that quasars at higher redshift seem to be more luminous. And so you again, are seeing a peak in the density of them. But this is sort of the regime where the host galaxy starts to become a problem. And so quasar surveys only really probe this end of the luminosity function, and you can see that this is a Schechter function, and so if you integrate this up, most of the integral is going to come from this, not this. And so essentially, if you're only probing to the knee of the distribution, you're missing a large fraction of the population. And so if you then make that extrapolation, you're going to have problems. Ideally, you want to probe this regime. If we convert this optical absolute magnitude to an X-ray luminosity, this is about 10 to the 44. And so we saw that the X-ray surveys can probe down to 10 to the 42 pretty easily before host contamination sets in. So we can also weigh these black holes. And so you have a broad line. You can measure the mass of the black hole. And you can see that the quasars are growing rapidly now versus in the past. And so they have a higher accretion rate now. They're now at its accretion rate of 1 to 10, or maybe a little bit down to 0.1. And so this is the epoch. Redshift 2 is, where 1 to 2 or 3 is when black holes were growing most of their mass. And we see them today kind of as dead objects in massive elliptical galaxies, which are kind of dead objects. So it makes sense. There's no gas to feed the stars. There's no gas to feed the AGN. We can also use X-ray surveys, either wide ones or narrow ones. And we have 1,000 times larger AGN space density than optical quasars. So a much better sampling. And so we can make luminosity functions in the same way. And so here's 10 to the 44, which is, these are the quasars. And so that this agrees relatively well with the quasars if you assume an AGN obscuration fraction, a type 1 to type 2 fraction. But now you sample this, and you can see that it has some evolution here. It's not flat, it's rising. And so there's a dominant component coming from this. So there's lots of low mass black holes that are accreting pretty rapidly too. And this is a function of redshift. So you can see that this shifts the same way the quasar ones do. So you can again play this game of, are these black holes growing more rapidly now than in the past? And in fact, these ones are growing less in the past than now. So these are more sort of normal common AGN, but they're lower mass AGN, and they're not growing as fast. And so we're actually seeing what we call downsizing, which also is seen in the stars. But effectively, bigger mass black holes grew earlier than lower mass black holes. They grew faster. And so this is a sort of property of the AGN that we need to explain. OK, so this sets up our sort of discussion of evolution, which will come tomorrow, and eventually black hole seeds, which will come off of that. Any questions?
Questions?
About the detection of AGNs using the variation, you said that you take an image, then you take another sometime later.
So 3 days later, you take an image of the same object, and you take the difference between them.
So the time?
Yeah.
3 years, months, days?
Well, I mean, you can do it as often as you want. But if you recall from yesterday, the structure function suggests that the longer you wait, the bigger the variation will be. And so if you want to take it 3 days apart, you have to have very sensitive observations to see small changes in the flux.
But the variation can go up and down, so you can take the image on an AGN with X luminosity, and sometime later with X again, then you will vanish.
You wouldn't see it.
Yes.
Yeah.
So you can control this.
No, you can't. I mean, the AGN is doing what it wants to do, and you picked a cadence that got you unlucky. You can model that, and so you can estimate how often that will happen and correct your data for it in terms of numbers of sources. So you can make simulations, do Monte Carlo simulations, whatever, to figure that out. But it's a completeness correction that you would do. But yeah, you can see it go down or go up, and so the difference image might be negative or it might be positive, depending on what it did that day.
Yeah.
The more samples you have, the easier it is because you build up signal noise.
More questions?
too early in the morning? You guys are hungry, thirsty?
Sure, everything's clear. We can continue discussion at coffee. Okay. Thanks again, Franz.